Where a position vector is a vector whose initial point is at the origin, a displacement vector can be a vector whose initial point is anywhere. So we have these two position vectors. The first vector u, whose terminal point is 3, 5, we know now that if we want to write that in terms of I and j, that would just be 3i plus 5j. And the vector v, which has a terminal point of -2, -7, would just be -2i minus 7j. But what if we have a vector whose initial point is not at the origin? So a displacement vector is that type of vector that has an initial point that is not at the origin. So this vector right here, its initial point is 3, 2, its terminal point is 7, 5. Basically, any displacement vector can be shown to be equivalent to some position vector, some vector whose initial side is at the origin. And we're going to do that by breaking that vector down into its horizontal and vertical components, basically finding the scalar values a and b. We're going to show that a displacement vector whose initial point is x1, y1 and whose terminal point is x2, y2 is equal to the position vector v x2 minus x1i plus y2 minus y1j. So we'll just draw a generic displacement vector. So we've got a vector whose initial point x1, y1, terminal point is x2, y2. So if I want to find the horizontal and vertical components, what I want to do is just draw or construct a right triangle from that vector. We know that A is going to be this distance right here. It's the horizontal component. That's just going to be the value of x2 minus x1. And B would be the vertical distance, y2 minus y1. So if I take this value A, I'm just going to mark off A right here, and I can mark off B right here. Right? A is just a change in x, B is the change in y. And if I take this new point, AB, this position vector, right, whose components are made up of AI, the vector AI and the vector BJ, that this vector right here, this new vector AI plus BJ, is going to be equivalent to our displacement vector. Right? We now have a vector that has the same length, it has the same magnitude. We've just basically moved it, right? We've repositioned it so that its initial point is at the origin. And we can do this with any vector. So let's look at example 3. We want to take a vector v whose initial point is 1, -4, and whose terminal point is 3, 5, and basically write it in terms of I and j, basically as a linear combination. So I'm going to draw the 2 points. So I've drawn my vector v, and I want to write v in terms of I and j. And I know that in order to do that, I need to take x2 minus x1, that would be my a value, so the coefficient or the scalar multiple of I, plus y2 minus y1, j. So that would be my value b, the scalar multiple of j. Right, so we just plug in our values. As long as you're consistent, it doesn't matter what order you subtract. So I'm going to get 3 minus 1 I plus 5 minus -4 j. My new position vector is going to be 2i plus 9j. The vector that is equivalent to my displacement vector is going to be the vector 2i plus 9j, which means I'm going to go over 2 and up 9. Initial point. Okay, this is v equals 2i plus 9j. Now, for this one, why don't we check, just to confirm, that these two vectors are equal, right? And if the two vectors are equal, we know that their magnitude and position have to be the same. So I know that the arrows, for both of them, they are pointing up and to the right. So we really just need to find the slope and the magnitude. Let's find the magnitude first. The magnitude of v is just going to be the square root of 2 squared plus 9 squared. It's going to be the square root of 85. And we know the slope, and 9 over 2, right? Your rise over your run. Let's check the magnitude on our original vector and the slope on the original vector. So the magnitude, 3 minus 1 squared plus 5 minus a negative 4 squared. It's going to be the square root of 2 squared plus 9 squared, which would be the square root of 85. The slope would be your change in y. So 5 minus a negative 4 is 5 plus 4 over 3 minus 2. 3 minus 1, which would be 9/2. So we've confirmed that this new position vector is equal to the original displacement vector.